So first up we have Stuart Bull. I think a lot of people know Stuart Bull, consultant for DGO Gold at the moment, and he has 20 years spent at Codes, very extensive experience in the African copper belt and said copper systems. So with that, I'll welcome Stuart up to give his presentation.
Thanks, Adrian. I'm a bit out of practice for public speaking with COVID, but at least I get to take my mask off. So there's got to be some slight advantages. Right, so a bit of an overview of DGO's sediment-hosted copper. DGO Gold's sediment-hosted copper on the Stuart Shelf. If I can work this. Just a little bit of a corporate overview. Basically, DGO exists to invest in and explore for high quality gold and copper assets in Australia, and they're currently active in South Australia and Western Australia. In South Australia, we're basically using exploration models developed in the Central African copper belt, and there the deposits are hosted in a Neoproterozoic basin succession that's quite similar to the Adelaide Fold Belt, and we're targeting classical sediment-hosted copper deposits. As an example of the sort of models we're bearing in mind, the most recent world-class discovery over there is the Kamoa-Kakula deposit. You can see the remarkable grades and tonnages there, and it's growing all the time. It's a Zambian type deposit, although it's actually in the DRC, and I don't have time to go into the subtle differences between the two. But importantly for us, it's hosted in diamictites that they call the Grand Conglomerate, but it's basically the Sturtian glacials, and you can see two photos there of beautiful chalcopyrite and bornite mineralization in diamictites that look identical to the things that we have extensively developed in the Adelaide Fold Belt. An overview, it's clearly one of the remarkable mineral systems of the world, a number of giant and numerous small deposits in an arcuate belt from Zambia up through the DRC, about 300 kilometres all told. My experience is based on two Amira ARC projects. I basically spent most of the 2000s working over there and somehow managed to live to tell the tale, and I've been consulting there ever since until COVID wrecked us all in one way or another. In terms of a quick overview of our basin scale models, the Katangan, which is basically interchangeable with the Adelaidean, the Katangan's the Neoproterozoic succession in Africa. The strata in the DRC, and I'm sorry I can't use a pointer, apparently it doesn't record, but that purple lozenge in the middle is the Katangan in the DRC. It's the central thick evaporitic part of the rift basin. It's essentially autochthonous, but it's been disrupted extensively by salt tectonics and then by Lithurium deformation when the Congolese and Kalahari cratons came together and closed the basin. The succession is condensed at the southeastern and northwestern basin fringes, and that's where the classical Zambian type deposits occur, and that's why you can have Zambian type deposits in the DRC and that northwestern corner of the system. In our hydrological model, and Adrian covered this a little bit, we would argue that basin-wide salt giants formed by a series of evaporitic episodes, and these led to the accumulation of dense oxidised saline residual brines that ponded in the Sin Rift phase footwall sandstones and probably interacted with basement. And from the various dates and styles of mineralisation in Africa, it's pretty clear that they were preserved beneath the top seal of salt and other units, probably for basically the whole basin history, and that probably explains the scale and longevity of the Central African system. In terms of mineralisation, we argue the ores formed during various stages of compaction and deformation related basin dewatering, affecting that central purple subsident part of the basin, and those events drove saline oil fluids up and out of the basin below the seal and led to the formation of the classical deposits in those intact basin fringes. In terms of timing, it's pretty clear that significant mineralisation commenced during or after hydrocarbon generation in those deeper, more subsident parts of the basin. So we would say it's mid to late diagenesis and possibly through to the onset of deformation. An example of a classical Zambian shale-hosted deposit, Chambishi Southeast. In that cross section on the left there, you can see the footwall clastics in the orange, and there's a little thin unit called the ore shale that's in brown that sits immediately on top of those footwall clastics. So the ore zones occur in that classical position at the lowermost redox boundary at the base of that ore shale unit. They occur above thin to pinched out examples of or areas of the footwall clastics, and basically there's a series of little half graben that control the footwall clastics onto a basement high, shown in the little cross-hatched symbols because it's granite there. And importantly, the ores, distribution of the ores, which you can see in the top right there, that's metre percent copper. You can see that they occur in what I call a transitional position between shallow water carbonates that sit on those basement highs that are shown in blue on the plan. That again, frustrating not to be able to use the pointer. And basinal shales to the southwest out in the more subsident part of the basin. And the copper ores shown in orange in both of those diagrams, you can see that they seem to occur in that interval between the shallow water carbonates and the deep water basinal shales. And I'll just expand on that, what I call the transitional zone concept, because I think it can potentially be applied in South Australia. It's a working hypothesis based on the distribution of deposits in that Chambishi Basin area in Zambia, but the caveat is that these are metamorphic rocks over there. The ore shale, so-called, and as a basin analyst going to Africa the first time, the first thing that struck me was this is called a shale, but it's actually a quartz carbonate phlogopite schist. So these are metamorphic rocks, but if we look at what we think's going on in terms of contemporary models, we would argue we're dealing with some sort of ramp with basement on the left and shallow water carbonate reefal and intertidal facies gradually transitioning, and it is a fairly gradual transition over several kilometres to tens of kilometres out to deep subwave based basinal shales at the right hand side of the diagram. Under that we've got the syn rift phase clastics transmitting oxidised saline copper bearing brines, but it depends how they operate depends on where they interact with those overlying strata. If they get up into the younger Katangan strata at the left hand side of the diagram, there's no reductants there to pull the copper out of solution. Out on the right hand side of the diagram, where you've got deep water shales, these seem to be relatively impermeable and tight, so you get a lot of anomalism on the contact, and that's exactly what we see, I would argue, in the Stuart Shelf. We see lots of anomalism at the base of the Tapley Hill Formation, but they don't seem to be able to get up into that tight, fine-grained rock and produce mineralisation of any thickness. What the distribution of deposits in the Chambishi Basin seems to suggest is that those transitional facies between those deep water shales and the shallow water carbonates are where the fluids can actually get up a bit higher into the stratigraphy and produce thicker mineralised zones. The facies are probably slightly coarser grained and more porous and permeable, and if there's a suitable reduced trap in that area, you can produce a decent deposit. So it's a bit of a balance between the left hand side of the diagram, where you might have lots of porosity and permeability but no reduced traps, and the right hand side of the diagram, where you've got lots of reductants but you can't get fluids into those tight rocks. So that's, in a nutshell, what I call the transitional zone concept. Moofolaria is an example of a Zambian sandstone hosted system. There's a lot of words there that I won't worry about. Basically what you're dealing with is those same oxidised saline ore fluids interacting with migrated hydrocarbons in classical sandstone petroleum reservoirs. Anticlinal traps in this case, and the anticlinal traps tend to occur where there are these sort of half graben architecture controlling the footwall. So once again you get a relationship between the ore body and thickness and facies changes in those footwall sandstones. So to summarise Zambian copper in a nutshell, all of the classical ore deposit styles occur at abrupt redox boundaries in the basin fringes. The reductants can be in situ in the form of shales or migrated in the form of hydrocarbons, and the footwall structural and sedimentary architecture are both important in locating high-grade mineralisation. On the right there's another one of the sandstone hosted deposits that my colleague David Selly did a lot of work on. The colours there from dark to light are the thickness of the footwall, and this is one of the systems where the ore shale is tight and it's forming a top seal and a blanket across that whole system. And you can see that the ore occurs in that classic stratigraphic pinch-out position against the basement high. Now you could stick that whole thing in the North Sea and it would just be a classical stratigraphic pinch-out hydrocarbon, probably a gas reservoir. So the Adelaide Fold Belt, fortunately Adrian has covered all this, so I can skip a couple of slides and get back on time. But just an important point though, if we believe the Snowball Earth theory, then we do have the Sturtian and Maranoan glacials, so we have direct timeline links between the Neoproterozoic basins. In Africa, the Sturtian's called the Grand Conglomerate and the Maranoan's called the Petite Conglomerate. And as I said, the Sturtian hosts a number of significant deposits, including that giant recent discovery in the DRC, the Kamoa-Kakula system. So it's a very important copper resource over there. And again, all this stuff's been covered. And I probably won't worry about that either. I suppose just in terms of a scale comparison though, that purple sort of lozenge that is the thicker subsident salt affected part of the Katangan in the DRC fits very nicely in the Adelaide Fold Belt. So in terms of scale, they seem to be quite similar. I think the fundamental question that we're all asking ourselves one way or another, and it's already been alluded to, is in terms of regional hydrology, did the Adelaide Fold Belt operate in any sense like the Central African Copper Belt, and have we therefore got potential for those giant high-grade deposits that occur over there? So in other words, were metalliferous brines of a similar evaporitic origin present in the main depot centre, the Adelaide Fold Belt? If they were, did they migrate out of that depot centre into the Torrens Hinge Zone basin margin at various times to produce mineralisation in that area? And if they did that, did they ultimately get to the more distal Stuart Shelf area where we can actually explore these rocks? If they didn't, it's possible, and it's possible they didn't because the lower Adelaidean strata pinch out, as shown in that cross section, pinch out in the Torrens Hinge Zone. We don't really know how because we don't have access to that, but once you get out to the Stuart Shelf, as has already been reiterated, we're basically dealing with Umberatna group rocks and some other restricted earlier Adelaidean strata locally called the Backy Point beds. So it's possible that the Stuart Shelf was actually hydrologically isolated from the main Adelaide Fold Belt depocentre and those saline fluids, and if that's the case, then we've got to appeal to different mechanisms to form the deposits out there. There's lots of smoke, so we think there probably are brines, and we've got, on the Stuart Shelf at least, we've got copper deposits that clearly have a sediment hosted flavour, and as in Zambia, we've got shale hosted and we've got sandstone hosted deposits. Now, I haven't worked on any of these, but there's no doubt I agree with the general consensus that they do resemble the classical Zambian deposits in some ways. They occur at abrupt redox boundaries, and when you look down the microscope you see similar replacement of pre-existing sulfides, usually pyrite, and you see the classic sulfur restricted zonation from pyrite to chalcopyrite to bornite to chalcocite, which you see in the classical deposits. The sandstone hosted systems, less is known about them, but I would just argue with my Zambian hat on that given where they are on that crest of the Pandura Ridge, that would be a classical site for the generation of hydrocarbon traps if you were generating any in the adjacent basins. The main differences, again these have been alluded to already, between what you see on the Stuart Shelf and what you see in Zambia. On the Stuart Shelf, the underlying oxidised saline aquifer seems to be the Pandura Formation, which was deposited in the older Karawelu Basin, whereas in Zambia it would be a Sin Adelaidean clastic sediment. So that's been mooted for things like Mile Creek, where the Backy Point beds are there, and so those earlier Adelaidean sediments still might be important, but in a general sense it's the Pandura Formation. And also, this has also been mentioned, we also get mineralisation at the upper abrupt redox boundary between the Tapley Hill Formation and the Whyalla Sandstone. So why did DGO choose the Pernatty area and how we're going to explore it? You'll see in drainage talk shortly that DGO supported a quite innovative geochemical study, and we got encouraging signals to get into that area. And wearing my basin analyst hat, I could see that sort of Pernatty Ridge architecture has a number of implications for sediment-hosted copper mineralisation. We've used the open file drilling to produce a regional facies map at Tapley Hill formation times, and the purple areas there are basinal, normal, thick Tapley Hill shale intersections such as Carmen talked about, and you can see the blue, there's a sort of a bathtub ring of carbonate locally called the Wukala dolomite around the Pandura Ridge. The yellow on that diagram is where I would say, based on the existing drilling, that we have potential for those transitional facies between those shallow water carbonates and those deep water shales that control the deposits in Zambia. So that's what we're targeting at DGO. We've got a company scale land position, and on that right hand diagram you can see we've got more than 250 kilometres of potential transition zone strata in terms of the strike length through our tenement package. And recent drilling of the Moseley area to the west of the Pandura Ridge has to some extent validated the concept. You can see the best copper grades there do indeed occur in that area where the Tapley Hill formation, I would argue, is onlapping basement, and there are carbonate equivalents to the right hand side of that diagram. The onlap relationship also means that we've got a shallow target in the area. I'm just trying to finish on time for you, Adrian. One handicap to exploration in the area is that while we can estimate the depth of the base of the main redox boundary target using existing drilling, we don't have any information on the architecture of the contact with the Pandura formation or any basal Adelaidean clastics that may be present. And these sort of relationships, as we've seen in my very brief sketch of Africa, are critical in localising the high-grade parts of the deposits. And we're going to test the efficacy of passive seismic to address this issue and try and give us some architecture on that redox boundary. And I'll finish there, hopefully almost on time.